This section deals with identifying linear and nonlinear functions and some types of symmetry. In a linear function, no variable is raised to a power other than 1. Any linear function can be written in the form of f of x equals mx plus b, or otherwise known as y equals mx plus b, where m and b are real numbers. So if you can write an equation in the form of y equals mx plus b, otherwise known as slope-intercept form, then it is going to be a linear function. We've already talked about some situations that are not linear functions. If you can't write it into y equals mx plus b form, then it will not be a linear function. It says a nonlinear function cannot be written in the form of f of x equals mx plus b. So there are some things that you should look for functions that are going to be nonlinear. For example, one of those is that you should not have a variable in the denominator. So if there's a variable in the denominator, it will not be a linear function. Now, it will be a function, but it won't be a linear function. If one of the variables has an exponent, so if you have like a y to the second power or maybe an x to the third power or any exponent on a variable, it will not be a linear function. If there are two variables being multiplied together, it will not be a linear function. And I'm going to add a fourth one onto here that's not written in the textbook, is if you're dealing with roots. So if it's something like y equals the square root of x, where one of the variables is underneath the square root sign, then it is also not a linear function. So in example number 1, it says identify or state whether each function is a linear function, write yes or no, and then explain. So if it's a linear function, we should be able to write it in the form of y equals mx plus b. So on part A, can we get it in that slope-intercept form? So if I subtract 3x from both sides, then I would get 2y equals negative 3x plus 8, and then divide by 2. I would have y equals negative 3 halves x plus 4. So yes, that is in slope-intercept form. It's in the form of y equals mx plus b. So this is a linear function. So we would write, yes, it is a linear function. And we would have to give a reason. And the reason for if it's a linear function, there's really only one reason that we can have here, is that it is in slope-intercept form. So yes, and the reason is it is in slope-intercept form. It can be written in slope-intercept form. Part B, is that going to be a linear function? And the answer is no. And do you recall why it's no? And it's because we have a variable in the denominator. Should not divide by a variable. And part C, is this going to be a linear function? And the answer to this one is also no. And the reason has to do with two of the variables are being multiplied together. Let's look at a real-world example. The graph models one prediction about the population of northern snakehead fish in a lake over time. The data in the table models a second prediction. State whether each is a linear function and explain. So Model A and Model B, Model A in green, Model B in blue, is Model A a linear function? And it looks like it might be a linear function, but actually I think that blue line is not a line. It is actually a curve. And we can see that it's a curve if we look at an actual line next to it. So if I try to draw a line, and this is a guaranteed straight line, I'm using the straight line tool, you can see that it doesn't quite be a straight line. I mean, you can see how it remains straight no matter where I put it. And I can touch a few of the points, but you can see it starts to kind of fade off to away from the blue. So this is not going to be linear. So this is not linear. And the reason it's not linear is you can see in the graph it is not a straight line. In the blue module B, we have a table, so let's just graph that in the coordinate plane down here below and see if they're going to be a straight line when we graph it. I think we can go by ones on the x-axis, so we would have 0, 1, 2, 3, 4. On the y-axis, we should go by something else. So it's your choice what you want to go by. You can go by 10s or 20s. 25s would actually work well because each one of these numbers is a multiple of 25. So I'm going to choose to go by 25s. So that would be 25, 50, and then the next one would be 75, and then 100, 125, 150. So I am still going by 25s per square. 175, 200, and you just have to make sure you have enough. The intervals are close enough that you can fit all the points on whatever shape graph and size graph that you have. So the first point is at 0, 100. So I'll place a point there. And then 1, 125 is right there. 2, 150. 3, 175. And 4, 200. So when I graph those 5 points, is this going to be a straight line? So can I draw a straight line through all those points? So I'll use the straight line tool that I have, and you can see that yes, I can hit all 5 of those points as a straight line. So yes, this is going to be a linear function, because it is a straight line. So that's the first part of what we're talking about, is identifying linear and nonlinear equations. The second part is to identify symmetry. The graph of a function has line symmetry. The graph of a function has line symmetry if each half of the graph maps exactly to the other half. The line dividing the graphs into matching halves is called the line of symmetry. We're dealing with what's called vertical line of symmetry specifically. And we're trying to figure out, is there a vertical line that separates a graph in half, so that if you can imagine folding the graph, it would fold perfectly into 2 equal parts. So on part A, can we take a vertical line and fold that graph perfectly in half? So the directions are, state whether the graph of each function has line symmetry. If so, identify the line of symmetry. So can we take a straight line and fold that graph, fold through that first graph in perfectly in half? If I can find my straight line, there we go. So if I draw a straight line right through here, let's change colors actually. I want to use a different color. There we go. Right through there. There's a red line. So yes, this does have vertical line symmetry. And then the second part says, identify the line of symmetry. So since it's a vertical line, we can identify the line of symmetry by writing the equation of a vertical line, which is always in the form of x equals, and then whatever the x value of every point of that vertical line is. And the x value of every point on this vertical line is always going to be 3, because in order to get to that red vertical line, you always have to go to the right 3 to get to it. So yes, it has vertical line symmetry, and it's x equals 3 is the name of the line. Part B is a straight line already, but does it have vertical line symmetry? And it is very tempting to say, yes, it does. You might think that the y-axis is the line of vertical line of symmetry, but if you think about folding it across the x-axis, what's going to happen? This part of the line up here is going to wind up going this direction, and going this direction. And then this part of the line down here is going to wind up folding over and going this direction, which means it's not folding on top of itself. So this is a no. It does not have vertical line symmetry. 3A and 3B ask the same questions. 3A, does it have vertical line symmetry? And that is a no. You cannot fold that across any vertical line and have it fold on top of itself. 3B, does that have vertical line symmetry? Yes, that one does. It does have vertical line symmetry. And if we go right through the vertex of the line and draw a straight vertical line through it, it does fold over itself. So then what is the name of that line? So it would be x, not y. X equals, what is the x value of every point along that line? The x value is always going to be -2. So the name of that line is x equals -2. The other type of symmetry we're going to talk about in this lesson is called point symmetry. In geometry, you may have heard to something called rotational symmetry. They're very similar. The graph of a function has point symmetry if it can be rotated 180 degrees about a point so that its rotation maps exactly onto itself. The point that acts as the center of the rotation is called the point of symmetry. So if we can spin it 180 degrees, which is a half turn, if we can turn it 180 degrees and it looks exactly the way it looks as it started with, then we would say it has point symmetry. So example 4, the directions are to state whether the graph of each function has point symmetry. If so, identify the point or points of symmetry. So part A, if we spin that round 180 degrees, does it have point symmetry? If you're watching this on a phone, you could probably just turn your phone upside down if you lock the screen, or if you're watching this on a laptop, maybe you can turn your laptop upside down. You would see, yes, it does have point symmetry. If you're watching it on a desktop, it's not so easy to do that. So what I'm going to do is I'm going to go to another screen. So here's the exact same graph blown up. And if I spin that round 180 degrees, does it look exactly the same? So I'll spin it around a half turn. And notice when I do that, it does look exactly the same. I'll do it again. So this is where it started. And then spin it around again, a half turn, 180 degrees. It looks exactly the same. So yes, we would say this does have point symmetry. And then the second part of the question is identify the point or points of symmetry. So what acts as the center of the graph that we would spin it around? And it's actually on this graph, it's right there in the middle at 0, 0. Now it's not always at 0, 0, but in this case it is. Part B, does this have point symmetry? Can I spin it around any point on this graph and expect it to look exactly the same if I spin it around 180 degrees? And if you try to spin it around the vertex point here, a halfway around, you're going to wind up with a figure that looks about like this. So this is no, it does not have point symmetry. A couple more examples down here. 4A, does that have point symmetry? If I spin it around, it's actually my upside down U is going to wind up being a right side up U going off my graph. So this is going to be a no. And 4B is a line. Now lines can be a little tricky because you might think that it may or may not have point symmetry. It does have point symmetry. So if you take a line and you spin it around, think about it as being like back in elementary school when you would spin a ruler around on a pencil. The line will look exactly the same if you spin it around 180 degrees. So yes, this does have point symmetry. The second question on that is, where is that point of symmetry? And you might think, and I hear this a lot, is that I hear people say, well, I'm going to go to the midpoint. But we got to think back to our geometric definition of a line. Lines go forever. So if lines go forever, how can they have a midpoint? It's not like a line segment where a segment has endpoints in geometry. Those arrowheads at either end means the line goes forever. So there is no midpoint. So I will just go ahead and erase that and tell you that the center of the graph doesn't really exist because it goes on forever. So it would have point symmetry, but the point of symmetry would be any point on that graph or any point on the line.